Hello, welcome everyone. I'm Beth Machewski. I'm with the Illinois Sustainable Technology Center. That's part of the Prairie Research Institute at the University of Illinois. To begin with, as a land grant institution, the University of Illinois at Urbana-Champaign has a responsibility to acknowledge the historical context in which it exists. In order for us to remind ourselves in our community, we will begin this event with the following statement. We are currently on the lands of the Peoria, Kaskaskia, Piankashaw, Waya, Miami, Muscatine, Odawa, Sauk, Meskwaki, Kickapoo, Potawatomi, Ojibwe, and Chickasaw nations. It is necessary for us to acknowledge these Native nations and for us to work with them as we move forward as an institution. Over the next 150 years, we will be a vibrant community inclusive of all our differences with Native peoples at the core of our efforts. This webinar and all of the Illinois Sustainable Technology Center's webinars are certified green events through the University of Illinois Institute for Sustainability, Energy, and Environment. To find out more about certified green events, please visit sustainability.illinois.edu. To find out more about the Illinois Sustainable Technology Center's webinars, please visit istc.illinois.edu/events. So a couple of housekeeping items before we get started. Today's webinar is being recorded. The recording and slides will be available online in a couple of weeks. I'll be sending out an email for everyone who registered for the webinar once those are available. And then for the folks in the room, if you want to be added to that list, send me an email and then I'll distribute that to you. For the folks online, you'll be remain muted for the entire webinar. And then we'll take questions at the end. For the folks in the room for the questions, you need to speak loudly, like I'm speaking, or like you're talking to someone across the street in order for the recording to pick up your voice. And then for those of you online, you can either type in your questions through the Zoom chat box, or you can unmute yourself and ask your question. Okay, so with that, I'm pleased to welcome today's speaker, Nimir Elbashir. Nimir is the director of Texas A&M Engineering Experiment Station Gas and Fuel Research Center. The center is a major research center with 30 faculty from the College Station and Mars campuses of Texas A&M University. He is also a professor of chemical engineering and serves on both of those campuses. His expertise in research and teaching experience from 4 countries worldwide, and his research focuses on designing advanced reactors and catalysts for natural gas and CO2 conversion and decarbonization. Nimir has received $17+ million in global research collaboration and holds several U.S. patents, European and international patents as well, and has many scientific publications. So, Nimir, thank you for joining us.
Thank you so much. Very grateful. Thank you so much, first of all, for inviting me, Kevin, and Hafiz to visit this center, which is a very distinguished in this critical area currently that's essential for us to move in the area of decarbonization. And the contribution so far that I learned is quite impressive. The facilities, the researchers, the core focus areas, as well as the level of the project. So, and it's my pleasure to be for the first time over here. I visited Chicago, Illinois several times. I had a collaboration, as you were going to see, with Northwestern. Sadly, even the center of Chicago, very recently, I have seen the center of Chicago. Normally, I come from O'Hare. I drive directly to Evanston, to Northwestern, and then I can fly back again, whether to College State to Houston or to Doha. So normally, as I indicated to the colleagues, and I receive a lot of questions, I introduce myself at the beginning whenever I teach any class new. So since I really hope that it could be And it will be a long-term type of collaboration between us. Let me introduce myself properly and my background. So, someone interestingly born in Russia, in Moscow. My father was a chemical engineer. He did his graduate studies, undergrad and graduate studies over there. And I leave this photo in Moscow with my mother. Then I'm originally Sudanese, from Sudan, from Africa, the heart of Africa. I studied my school over there as well as college, university called University of Khartoum, built on the British colony heritage, built on the University College London and Cambridge, and until the 1980s, the exams came directly from Cambridge to many of those schools. Then I was supposed to go to Cambridge, but sadly, due to political reasons, the Sudanese government kicked out the British ambassador. After we got the scholarship and they canceled the scholarship, I did my master in Malaysia, in a city called Johor Bahru University of Technology, Malaysia. It's now one of the top. And it's across the street from Singapore. You can see Singapore in the other side of the city. Then after that, I was supposed to continue to the PhD, but I decided that I need better exposure to the industry. And I came and I worked in the academia industry, company called SABIC, if you are familiar with the petrochemical type of industry, it's one of the largest petrochemical. Then I came to the States to study my PhD at Auburn University in Alabama. And then after that, I decided to go back again to the academia, which is bringing me back again to the Texas A&M experience. In the family side, this is my family. And I have 3 kids. The tallest one is the one in the center. Okay, this is the youngest one among them. She is right now a junior at Yale University. She's studying political science and economics. The shortest one is the eldest one. And this is Obon Gale, by the way. This is Johor Bahru Gale in Malaysia. Okay, this is the eldest one. She is now doing her PhD at MIT. She's in her 4th year. She's in cancer biology. And then my son here in Riyadh, Saudi Arabia. That's the one in the middle. That's in between them. And he graduated from MIT as well, computer science, and he did his master there. He's right now working those. They are as smart as their mother. So it's not, I cannot claim any credit in this. It is their mother's kids. Their mother is a very smart doctor. She's physician, pediatrician, actually. Now senior consultant in pediatrics emergency. So when we go to any immigration officer, normally we have to explain how a family of 5 that's born in a different continent and a different countries. When we put our passports, we are all US citizens, so we have to do some explanation when we come together. That's normally make joke of us. We are together. Okay, so in case of our backgrounds, my backgrounds in the industry is the one that's led me to this kind area. I work in Saudi Arabia with SABIC in the oxidative dehydrogenation catalysis. And I was talking to your colleague here about how this was a critical part of the catalysis work that we have done to the transition of a certain area of catalysis. Then, after my PhD, I worked with BSF in Esalen University, Research and Development, and it was corely focused on the environmental catalysis. So the environment is the center of what I do. So all experiences that I have exposure, both in academia and industry, related to the environment, and also related to the energy sector. So we are in a world that we are expecting a significant growth in population, and mostly this population, by the way, is coming from Africa. You can see I'm originally from Africa. And that growth in population will require energy, a significant amount of energy. So in my village where my father born in Sudan, and it is not far from the capital, until in the middle school, they do not have electricity. So they were enjoying their life and everything is organic. But now when we get to college, then they have starting the electricity, and then the requirement of the developing nation of energy will gonna be more significant than for the developed nation. And therefore, we cannot claim that we will gonna survive with what we have right now from the energy resources. So the energy resources we have is quite limited. and still fossil fuel playing a very critical role of that energy. And there is no expectation, by the way, regardless of all the push we are doing right now, there is no expectation of any dramatic change of this distribution of energy, whether currently or as the forecast in 2050, where we are expecting a lot of things to happen. But we will notice two things. Yes, there will going to be a significant growth of renewable, but natural gas will start taking over significantly from coal and from oil. Nevertheless, the quantities will going to stay the same of those. Even though if we switch, still their percentage will going to be lower, but their quantities may even increase. And all of this is a burden on us who are dealing with this decarbonization issue. Why natural gas is important? Because natural gas is much relatively cleaner than coal and oil. And at the same time, we started to learn how to deal with it and how to handle it. And by the way, starting from COP18 in Paris, there is general agreement that natural gas is the transition fuel from the fossil fuel to the renewable sector of energy. So how we can do this? This is a question. So now, even though we are seeing improvement, by the way, in the reduction of emissions that's coming from coal and from oil, but we are seeing to some extent an increase of the emissions coming from natural gas. And this is simply now because we are using more of it. Yeah, now we are becoming more aware of the emissions coming from fossil fuel, but we need to do much more in order to handle the current situation that we are facing in this process. And that's require a major focus. For the first time in the last COP meeting, there is such a statement that's come, that's in the United Arab Emirates, happened last year. Transition away from fossil fuels in energy system in a just, orderly, and equitable manner, so that we can have those renewable energy sources will be taking over. But we have to guarantee this. So sadly, I got disconnected. So now let's hope for the best. Okay, so yeah, this where I participated in this conference, I participated with those natural gas forum countries as well as different entities. The core focus is how we can do this. Is this really achievable or not? Technically, because they brought us as an exhibit that's working in the natural gas industry. Why natural gas is important? Because the countries that's controlling the natural gas, both in terms of production as well as in terms of sending to the world, are a limited number of countries, unlike the oil. So Russia is leading the world in terms of having the highest reserve of natural gas, but the United States is taking the lead in terms of the production, by the way, as well as now the United States, we're going to see how it really transformed. And then a small, tiny peninsula that's even the smaller than the smallest city you have over here, called Qatar, is number 3. It's directly after Russia and the United States in natural gas. And by the way, Qatar is using its natural gas control of the global market in 2 major forms. LNG, liquefied natural gas, which is they make the gas liquid and transform it around the globe. And they are leading the world. And also they are expanding more and more, but followed by the United States. And normally the United States here become the leader now, even in the liquefied natural gas, and they are expected to have a major transformation in the industry of the natural gas, specifically in the LNG. You will see why this is important. This is very critical. I'm teaching a course for Texas A&M students since 2015, and I'm teaching them about the natural gas globally and how it's really distributed. Okay? So I keep telling them that the United States still consume all of its natural gas internally. The shale gas booming changed the map completely, and now the United States become a major player in the LNG globally. From none in 2016, now they are leading the world. They have the highest capacity, and by 2027, they were going to have the world highest capacity LNG capacity. Okay, and this is where does it exist. Most of the new plants in terms of liquefaction of natural. What does that mean? That means a significant investment in something we call it midstream natural gas. Natural gas is composed of three elements: upstream, midstream, and downstream. That midstream wasn't very significant in the United States because most of the natural gas we have here, we use it in power generation. We don't need to clean the gas or we do anything with it. So we do not have midstream that produce a significant amount of component that we have to deal with, and specifically CO2, because now we're going to strip the CO2 and the sulfur and everything so that we can produce pure methane. We can use it for the LNG capacity over here. And that's a big deal, by the way, and a big opportunity. State of Texas, we are leader in terms of the natural gas capacity, obviously followed by Pennsylvania and Virginia in the Marcellus field, which is at the shale gas booming in those areas. But what did that mean? Now we have to figure out how to do this distribution properly. And if we need to decarbonize, we cannot only decarbonize one sector. We cannot say, hey guys, we'll wait until we get it. And then whenever we use that natural gas, we're going to decarbonize it. We have to decarbonize it from the well all the way up to the wheel. And we have to ensure that all of those sectors is decarbonized and we can manage how to handle this situation. And that's not an easy deal, by the way. So the transformation to hydrogen become the story, become the core focus. And natural gas is still a source of 70% or more of the United States hydrogen. Steam reforming of methane is still the major source, even though now we are pushing heavily towards the green hydrogen. And the hydrogen industry is also quite complicated and has to be very well integrated from the source all the way up to the utilization sequence of the hydrogen. And that's also another opportunity that we have to think about how we integrate all of those together to ensure the decarbonization, even for the green sources, is not an easy target. I believe you are all familiar with this color coding of the hydrogen. Okay, the one we get from coal, that's a major emitter. That's for each 1 kilogram, we're going to get 20 of CO2 is the black one, the gray one, the one from natural gas, which is a common one, steam reforming of methane. If we capture the CO2 and we sequester, and that's the core distinguish your center over here, then we can call it the blue hydrogen. And then we have the green one, and we have the other courtois one, which is the nuclear one. You will see later in my talk that's what other opportunities we can make in order to survive this blue hydrogen even in a better situation than the others. Okay, so the United States, sadly, is number 2 in terms of the CO2 emitter after China. We all know that. So there is a huge investment from the Department of Energy, and you are very successful in establishing it in order to handle this situation, and this also in order to the transformation of the hydrogen. After exactly the shale gas booming, Texas A&M decided to build the Gas and Fuel Research Center. Texas A&M, we were the leader in the area of the oil, and our petroleum engineering department is very well known, and that's our strength areas. And then when the shale gas and shale oil boom came, then Texas A&M thought of how we could really capitalize. Meanwhile, we look at the problem from the source until the end of it. And I had the pleasure from 2015, the Board of Regents of Texas A&M built that center and to be the lead of the center that's operated both in our main campus in College Station as well as in Qatar. At that time at Qatar, we built a very unique collaboration models with the industry that also existing in the state of Texas, working in this natural gas processing. So we have petroleum engineers, we have chemical engineers, we have mechanical engineers, we have safety, we have material, we have chemists. We are a combination of multidisciplinary working in trying to advance the natural gas production and processing. The shale gas in the state of Texas, and in Qatar, we have something we call it non-associated natural gas, a reservoir that's basically natural gas. The characteristics are different, and therefore our goal is how we find a connection between the upstream, midstream, and downstream to ensure that we can decarbonize the industry. And that's, by the way, very unique. And we are working in a completely different types and properties of industry as well as types of natural gas. So that gave us a very unique opportunity. This is the state of Qatar. The shaded area outside, this is a non-associated natural gas, which is the same size of Qatar itself. It's not associated, this is the reservoir where all of the gas that Qatar now depend on and become #1 leader almost in the LNG capacity right now. And then also in pipeline infrastructure that you can see the pipeline going to the United Arab Emirates from the overall structure. So Qatar is a peninsula that's connected only to Saudi Arabia with land. Okay, so now how they utilize, how they monetize their natural gas. They have done it in a form that's when I teach my class, I tell them there are 3 properties of natural gas monetization. Property 1, use it locally, like the United States. Property 2, you transport it globally. You have 2 means: pipeline, like Russia, all the network to Europe, or through LNG. And LNG, you make it liquid, you reduce it by 1/600 its original volume, and you ship it. And when you get there, you turn it back again to liquid. And then the hydrogen. So they have done the 3, but not the hydrogen. In the United States, we have the hydrogen as a part of the game. So how we deal with this problem on decarbonizing the natural gas industry so that the hydrogen will gonna be a hydrogen that's suitable and comparable to the green hydrogen. And that's the question. So that midstream plant, which wasn't existing in the United States until recently, become the issue. And this is the core focus area of my research team. As a center, we work with the industry, we work with academia. Now we are coming to a very distinguished center here, exploring opportunities of collaboration. We collaborate globally, by the way, and we work with industry, whether they are existing in Qatar or existing in Texas or even global-wide. And then we are trying to make an impact in terms of technology development and processes. And this is a sample of some of the companies that we are working on. The funding that's came to us is coming from different resources, and this is part of it. Let us come to the technical talk of the story, the CO2. So the CO2 is our nature. It is existing there. Okay, and the nature know how to deal with it. And the nature is handling around 750 gigaton per annum of that CO2. Similar to the air, similar to whatever we have around us. Nevertheless, our utilization of these fossil fuel resources brought this 37 gigaton per annum of CO2, which become the whole burden of the global warming, even though it's very small compared to the one that the nature dealing with. So now we are struggling to figure out how we capture it, which is the core focus of your team, and for us, how to utilize it, how we put it in the map. And if we look at the comparison between the two, we will find the following. That's the CO2. We have several options to deal with it. We either eliminate it by trying to find 100% renewable sources that we can deal with, or we will gonna need it, then we have to figure out how to recycle, reuse, okay, to some extent, store this amount of material that's composed of the greenhouse gas emissions. And that's the real issue. So if we look at the comparison between the two options, the capture, which is your core focus area, right now, obviously we're gonna need energy. And therefore it has cost. And it will gonna need the subsurface and the geology that could really help me to store it. So, and it's growing. And I believe that indicates clearly you are in the right path. If you look at the figure blue, it is here, it's showing clearly that it is. What is the advantage? The advantage, it is scalable, but economically challenging because those guys will gonna only pay money to capture it. They pay money to compress it and to find the reservoir, and then they get nothing out of it. The second one, which is, we call it enhanced oil recovery. Obviously, it makes sense for the oil companies, but it doesn't make any sense for the environment because they will take the CO2 and then they will gonna produce more oil. That will gonna emit more CO2 than the CO2 they put on the subsurface. And therefore, it makes sense to them economically, but nevertheless, it doesn't make sense to us, but it's still scalable. The one that's challenging is the utilization. because it is tiny, small, very small yet. And we have a significant amount of CO2. And we have to be really very clear in the path on how we can build this CO2 utilization map. And this is the work of my research team. So we try to understand, if we go to the utilization, which is the best path that we can use so that we can go for the utilization. Okay, because we have to be very careful. So far, urea using CO2, am I right? Methanol using CO2, but nevertheless, still in their quantities extremely small. So we need to develop techniques. Those techniques were going to help us to see which path we go and what is this path we're going to do economically, as well as in terms of CO2 fixation. Because CO2, in terms of carbon and oxygen connection, that's going to require a huge amount of energy to break it, am I right? And if I got this energy from fossil fuel, I may be emitting more CO2 than the CO2 I'm using in the process itself. So trying to measure this is very sophisticated work, and I have my PhD students who is currently at MIT Energy Initiative, GASIN, who conducted those type of development and assessment, and he have done it as well with MIT Energy Initiatives in collaboration, have done it in collaboration with them. The techniques that he has done is the following. We need to understand the chemistry. We need to understand the energy requirement in order to do the conversion of the CO2 in the process. And then we need to understand how we will going to handle it as the process goes. And finally, whether it makes sense economically or not. So it will going to be hitting two dimensions in terms of the process. I will going to very briefly describe it to you. So if we have a very simple chemical reaction, and that simple chemical reaction, that we are utilizing CO2 with methanol in order to make carbonates, okay, DMC. Whether this chemistry could be considered CO2 utilization or not, that's the question. So what we will gonna do, we're gonna first say that this CO2 fixed parameter that we develop, it is actually the CO2 fixed through that chemistry divided by the CO2 produced by the energy requirement during the process. So if it is 1, okay, but if it is less than 1 or more than 1, that's going to be the story. So if it is 1, it is total fixation of the CO2. So we're going to look at the chemistry. We're going to see how much heat required for the chemistry, then how much conversion we will be able to achieve, and how much energy required for this process. And this energy will be coming from the reaction, coming from the heating, and coming from the compression of the process, because those are gases. Then I will account all of those relevant to the conversion that I could achieve in one reaction. And when I look at it, I will get to know exactly whether I am really fixing the CO2 or not. But we added other parameters to the process. So what are those parameters that we added to the process? We are trying to understand the extent of the energy integration. Could we reduce the energy requirement through energy integration or not? And then whether the efficiency of the process in terms of the energy source could really impact that this CO2 fixation or not. And also the energy intensity of the overall process. So we inserted all of those parameters. And when you see the source of energy, it can show you exactly the diversity. So if I do this chemistry using coal, the story is completely different if I'm doing it using wind. And even the wind offshore different from the wind onshore, and so on. So that's from where you get the energy is a very critical element of telling you whether you really can save this or not. That the process at the end that we develop in terms of the efficiency and the intensity of the reaction, that could tell us, and that's, as I told you, has been done in collaboration with MIT Energy Initiative. In a typical process, you look for several chemistries, you look for different sources of energy. You show here that all of those based on fossil fuel, you may barely get to fixation if you are so lucky, even if you are using CO2, because you are in this region. But all of those with renewable, you can get to even higher fixation. So it's an encouragement that even if we want to take CO2 utilization, it's better to take it with renewable energy. And this is a quantitative. And when you look at a conversion like a chemistry dry reforming of methane, I will speak about it in the remaining of my talk, this will show you exactly how we could make the difference of the process. So the process, we're gonna have two elements: experimental, to understand how the process works, and develop as modeling side in order to account for the potential of CO2 fixation of those processes. So let me take you to one example of natural gas. And that's not common example, but that will show you exactly how we use our know-how in those areas. So we work in the gas processing research in an area called gas to liquid technology. In the gas to liquid technology, we take natural gas, we make liquid hydrocarbons out of it. This is a competing monetization technology with liquefied natural gas, which is make physically the gas, which is methane, as liquid by cooling. Mechanical engineers brilliancy. We chemical engineers make it gas to liquid technology. We take the gas, we make it syn-crude, similar to the crude oil. I guess similar to the area that you're working. So you're gonna see some similarity over here. So this process is composed of 3 stages. The first one, reforming, how we reform natural gas to make something we call it syngas, hydrogen and carbon monoxide. This reforming is the same process that makes hydrogen, which is a steam reforming, but it could be other reforming. And then we take it to a chemistry called Fischer and Tropsch, developed by the German scientists in 1920s. And then we produce syn-crude. This syn-crude is white compared to crude oil, but have the same hydrocarbons. And then we refine it and we produce a final product. If we look at it from the flow chart of the process, this is how does it look like. This is the flow chart of the process. And it composed of the 3 elements, okay? If we look at which one is the most energy intensive, it is a reforming. Breaking that methane, again, we're gonna require a significant amount of energy. We're gonna require temperature higher than 1000 degrees Celsius. And if I go to this temperature using fossil fuel, my emissions will gonna be significant, okay? This is the first step, and it's a major step in the process. So how we can deal with this process, how we can handle it. My research team work on the 3 pillars. And that's where we learn how to decarbonize the process, by the way. And this decarbonization of the process is very critical because the future reformer globally will gonna be cane. This reforming and refining plants and chemicals industry that built on crude oil in the future will not gonna be existing by 2050. It has to be transformed to biomass as a feedstock. It has to be transformed to CO2 as a feedstock or whatever waste. And I guess you are working in all of them. You can work. You have very strong contribution. That's I followed today and enjoyed listening to in the biomass work and how you process it to fuel. And then also you are working in the plastic and plastic waste and how to be going through the pyrolysis. And then you are capturing the CO2. So the complementary part of how you really build that network that will then transform. This is the Nature paper. And this Nature paper, actually from a group in UK, the Department of Energy considered it as the starting point of any work to design the future refinery plant. Has to be started from here. They were not gonna accept anything that will take crude oil or take gas, whatever. And here we are trying to see how we could really be relevant, how we could really meet all of those standards that will be part of this story. So you can see that different refineries will gonna take different products. And I will tell you the story from the end. The fuels that we make. So I will show you exactly how we work in this area, all of it. So the final fuels, and that's an interesting project. We work with Shell, we work with Rolls-Royce, with Airbus to design synthetic paraffinic kerosene that's coming from natural gas through the gas to liquid technology to replace crude oil that's coming from the, or kerosene or jet A1 that's coming from crude oil. So this was a very interesting consortium, by the way. So I have the fuel characterization lab, and my research team work heavily, and it's very unique set of characterization of understanding all the properties associated with the design of the fuel. and how different fuels and different fuel blend related to the hydrocarbon structure of the fuel, because the certification of each fuel will gonna require certain properties. When you meet those properties, ASTM will tell you we can call your fuel aviation fuel or not, or diesel fuel or not. Okay, so here we work very closely with the industry, and we have an ISO certified lab. That means the industry is using us, and I get a lot of money out of it, by the way. That's I hire a lot of students to work with me, and it helped me in many of the operation of it. I will show you a unique example from the aviation industry. The GTL fuel is very simple fuel. It's coming from paraffinic hydrocarbon, unlike the one coming from crude oil. Therefore, it looks like water. You cannot distinguish it. That water bottle in the back here, you cannot distinguish it from the GTL fuel. You cannot smell it either. Why? Because of two reasons. It has no sulfur and it has no aromatics. And that's make it like water. So, but the engine itself having been designed for that neat, very nice fuel. It's been designed for the fuel coming from crude oil. So when they ask you to certify it, you will tell them, my fuel is mainly paraffin, normal isocycle paraffin. They will ask you, do you meet the ASTM? Based on density, viscosity, heating point, etc. This is where we are specialized. Because in some of them, the more ISO, we need density. But if this is the freezing point is non-linear completely. That means meeting all of the properties is a big deal for those type of fuels. And that's an interesting area we work heavily on. And also we work heavily with GE and others, and also besides Shell in aviation fuel on the diesel fuel. So understanding those type of fuels and trying to insert them in the industry and to certify them is a very big deal. So the consortium with Qatar Airways allow us to support Shell in order and the others to certify something, we call it ASTM 7566. That means mix between jet fuel coming from crude oil and mix with the fuel coming from GTL, SBK 50/50 can be in the airplane, because the certification of the fuel in the aviation industry is very complicated, unlike our cars. Because cars, we can stop it and take Uber, all right? But in the airplane, if you have a problem in the over there, you're gonna be a big deal for the certification of the fuel. So also we work heavily on the catalysis in order to understand how those processes work. We design our own reactor systems and we scale them up. We start from the lab scale, we go to the bench scale in many of them, and that's a typical bench scale for the Fischer-Tropsch. So for the Fischer-Tropsch, we work with Cambridge, we work with Open, with the Virginia Commonwealth, but we work also heavily with the industry to help them see how they can control the selective control of the products that's coming out of this reaction. This is a polymerization reaction. Start with building block, another one come, and so on. But if you are interested only in gasoline, what you are gonna get and how you can control the process. So we have done a lot of hefty work in designing those catalytic process, and we move and we advance those catalytic process. The one related to the CO2. The most energy intensive process that I refer to, which is the reforming. This is the one at 1000 degrees Celsius and above. In Shell plant in Qatar, which is the parallel GTL plant, it is 1300 degrees Celsius, where they do the reforming process. See how intensive is it? So we told them we can advance a reaction called dry reforming of methane. Rather than reforming by steam or reforming by oxygen, partial oxidation, we will help you to commercialize reforming by CO2. Good deal? That's what we promised them. Then we need to prove that this process is a CO2 fixation process. Otherwise, it has no meaning, and it's energy. This process actually is very unique. It is existing for a long while, but no one was able to commercialize it, unlike the other reforming. So I led this consortium for 6 years. It's around $6 million consortium, $5 million coming from Qatar National Research Fund, beside $1 million coming from different sources, with Total Energies, Total Belgium, in Falloway, where the petrochemical, as well as Total Qatar, and then with Northwestern University. Over here, we work with the chemistry department, Professor Tobin Marks, Peter Ster, and Eric White. And then with my colleagues in the system engineering side, we are trying to solve the problem related to dry reforming. The problem as follows. Now for the reforming, we have two core carbon sources, CO2 and methane. Carbon deposition is very likely. The reaction is even more endothermic than steam reforming of methane. That means we're going to need more energy. And if I get this energy from burning fossil fuel, I will never get to the CO2 fixation. The very bad thing is that I'm going to have deficiency in hydrogen. The hydrogen to carbon monoxide ratio, the best I could achieve theoretically is 1:1. While in the downstream process, the least I need is 2:1. That means I need to solve. So what we promise them, we will gonna solve all of those problems, trying to address those issues from the micro scale all the way up to the macro scale. So we go to the core of the chemistry. We look at the process and we integrate all of them together. And we come up to solutions at the end of those 6 years. Those solutions addresses the problems that we started with. So with Western University, they work in designing very unique catalytic process protected by atomic layer deposition, building a layer of amorphous alumina on the active side so that we're not going to be contaminated by the coke and the coke will going to kill it. My research team designed a system of nickel cover system. The most important part is the reactors work. So we design series of novel reactor processes. Those novel reactor processes will then help to address the remaining problems, the endothermicity and even the deficiency of the hydrogen and carbon monoxide. I will focus for the sake of time only in one of them. Okay, so it has been a very successful consortium. We have more than 30 journal papers. Okay, as a consortium, that's a very big deal. We have more than 6 PhD students graduated, 20 masters, and so on from different universities and institutions. But this uniqueness of the patented technology for the CARGEN is the most important element. But this is a model that those students have an exposure of going to Evanston, is spend time going to fellowing in Belgium, working and getting that type of exposure of collaboration and big groups has been a very unique type of work that has been done in a very integrated way. This CARGEN process or carbon generator reactor, which is a collaboration we started with right now in the DOE proposal, that's we hope it will going to be successful and will take us to move forward. Let me explain it to you. The process is started with an idea from this student. You're going to later, he was my PhD student. Okay, he's right. I just a couple of days ago, I have lunch with him in Chicago. He is now in Honeywell. Okay, and this guy is come up with this brilliant idea. In the project, we are trying to avoid carbon formation. This is one of the major killer of the catalyst. He said, let us make carbon in one reactor and make the reforming in the second reactor. And it was just whatever idea. Okay. So what we end up with a technology of 2 reactors. The energy requirement of it is almost half the energy requirement of the dry reforming of methane. Close to what we tell. The CO2 conversion, because of those 2 setups, can go above, well above 65%. Then we will never be limited by 1:1 ratio. We can go in the second reactor to whatever hydrogen to carbon monoxide ratio. The more important element. Now, in the reforming process, we're producing 2 products. Solid carbon, that's high quality carbon, multi-wall carbon nanotube, and we can produce syngas, which is a reforming, original reforming for syngas production. And you will see how the impact of this will gonna work later on. So this CARGEN technology, which is CAN, I will show you exactly how it developed from the inception until the scalability level of this technology in terms of a process. So the concept again is come from this student, and I asked him with my colleague, Professor Halwaji, in the process system engineering, we told him, yeah, do thermodynamic calculation, see exactly what is the requirement of the energy base for this process. So at the lowest energy, we formulate the most amount of carbon. Therefore, in the real reforming, we do it at a very high temperature. So that's to avoid carbon formation. So we go in this rate, there is no carbon formation. Am I right? So the catalyst can survive But in this range, we burn a lot of fuel. The CO2 emission is the highest. So we pay for one cost for another cost. So he have done it at this, which is autothermal almost, and he produced the most carbon. Then we came and we said, let us do it experimentally. Let us go and see whether this is really real and what type of carbon. We never intended to produce carbon nanotube. This was not the intention. The intention was to get wherever carbon material and get rid of it as a solid carbon. So what we notice when we have done it in the micro level, in my small, excuse me, type of reactor, what we notice, that's the carbon, multi-wall carbon nanotube. That's the microgram level. And then we start getting curious. Is that real or there's something wrong? Then I asked them to scale up the reactor and to scale up the process. So Dr. Sufyan and Dr. Hanif, who's a postdoc working in my team as well, they moved now to the TGA. Okay, and in the TGA process, they have done it in the milligram level. So we found that we can still control it in multi-wall carbon nanotube, and it's a deep growth mechanism that the catalysts go like this in the process. Then we change our strategy in the catalyst. At the beginning of the project, we are trying to use catalysts to avoid carbon formation. But now we are aiming towards carbon. So we have to switch the strategy to make catalysts that make most carbon in the process. And that's also part of the discovery of the process. Now we prove it in the milligram. Now we said, let us see it in the grams and hundreds of grams. Then they design a chemical vapor deposition system, which is a different regime of interaction, and we run the reaction. And if you see that the process will gonna accumulate of the catalyst, and then we will gonna make carbon nanotube out of this process. It will gonna be very clear over here. And if you look over here, you're gonna see that Dr. Hanif is pulling out this tube full of carbon, which is started with the catalyst and carbon nanotube, and it's still multi-wall carbon nanotube. Then we start playing with the protocol on how to ensure the quality of the carbon nanotube, depending on the protocol of the process. So we starting looking at whether we can make it kilograms level, which is what we observe at the microgram level. So at the kilogram level, we design a larger system of a similar process, and that's a carbon nanotube in terms of kilogram inside those tubes. So when you look at it, actually, this is a scientist that they are pulling, the postdoc and the PhD student, they are pulling the tubes out, and this is full of carbon nanotube, and that's a kilogram level demonstration of the process in the chemical vapor deposition process, and still it's a multi-wall carbon nanotube of high quality, not from us. All the third parties, they took it, all of those who want to collaborate with us. So what does that mean? Let me take you back again to the decarbonization story and to the natural gas process itself. This means the following, that, for example, in Qatar, and I was talking to Kevin earlier, they have a very unique structure of infrastructure. Most of the gas processing plants into industrial city. And the midstream, because they are producing LNG and they are producing ETL, they have to strip everything until the methane. The midstream is the largest existing. They have so many cranes in one place. Per day, roughly, they can emit 10,000 tons of CO2. And semi-pure CO2, because this came from the sweetening process. In the sweetening process, and they have sour gas, we remove sulfur and we remove the CO2. So here, how we could really, by similar technology like this one, we bring the midstream plant to the downstream side plant of the story. That this CO2, which is impact any carbon intensity of whatever product they sell, we can take it now and we can bring it to the downstream side to produce two things, syngas and carbon nanotube. And it will gonna be a full sequestration of the CO2 if we do it properly. So we look at gas to liquid technology, which is Shell have the world's largest existing ETL plant in Qatar. And also Sasol have the other one. That's also a smaller plant than Shell one. So what's the story here? The story here that this carbon nanotube has to be utilized, am I right? And if we start producing a large quantity of it, We have to find a utilization. Someone have to use it. And carbon nanotube is existing, but it is expensive to make. And it is cost, by the way, is around here. The cheapest one is around $100 or so per kilogram carbon nanotube. And if you go to the single wall, it can go to $10,000, even beyond that scale. And therefore, it is utilization is limited. But now with this process, we can bring it to a very large scale that it can get less than $10 per kilogram. And that will open for it a significant application side for this carbon nanotube, and that's going to be the sink of the carbon material produced in this process. So this is the core focus of my research team, on how to develop the technology to the scalability level, and then how to build the collaboration with the utilizer of this carbon material to be part of the process. You remember the color coding earlier? Now I will show you a very interesting hypothesis that's going to be a good story to come as a part of this. So we said we have two products. We have syngas, and the syngas, hydrogen and carbon monoxide. So we have hydrogen here as a product of this CARGEN process. So what the uniqueness about this hydrogen? So this is the coal we talked earlier. This is the steam reforming of methane from natural gas. This is the blue hydrogen if I capture and sequester the CO2. Still, we're going to have emissions. This is the renewable, and this is the nuclear, almost zero. It's not zero. There's nothing called zero. The material and the process itself is going to be emitter, but relatively, everything is relative. Our technology, with this way, using the CO2 to make this hydrogen from the methane, it could be negative carbon hydrogen. Okay, and by the way, we have done it. All the quantification process following our concept in the CO2 fix. If we look at this boundary compared for steam reforming of methane and blue hydrogen and coal, this is negative carbon hydrogen. That's another marketing value besides the marketing value of the carbon nanotube. And the carbon nanotube is actually a big deal, by the way, because it's a big process. So how we can maximize this hydrogen? And this hydrogen is a big deal. So we need to develop a systematic catalytic process for the second part of the reactor. So I have two reactors. I have the CARGEN, and I have the conventional tri-reforming of methane. So we have done a lot of work in developing those catalytic systems that even in the second reactor, we protect the catalyst from the Cook deposition. Okay, and that's a patented catalytic system. Then to scale it up, we need to understand the kinetics. Now our reaction in the CARGEN cover all the reforming technologies. It have the steam reforming. Because we have a little amount of oxygen, we have the partial oxidation. Okay? The steam, because the water is byproduct of the CARGEN process. And then we have the dry reforming, which is the CO2. And then we have the Cook formation over here. So we have all of those reactions. To capture what is really happening, we need to understand and to measure all of those reactions and validate their significance. And by the way, when we capture them, it really matches exactly what we observed in the experimental. Even the amount of carbon that we measure at the end of the process. That means the model is working. What does that mean? It means we can use it to scale up the technology even further when we go to the tons level of the process. Okay, so here we need to move forward. We have looked at it in the existing infrastructure to produce something relevant to sustainable aviation fuel and to compare it with even with the natural gas. And then we look at it in the ammonia process. Okay, I will not gonna bother you with all of those details. So we showed exactly how much we reduce in terms of the emissions and what is this impacting the carbon intensity of the final product that we produce. Finally, what is this material of carbon nanotube we produce? And what difference does it have from the one in the market? So this is our material that we produce all the way up to the kilogram, and this is what is existing in the market, right? So we have a longer diameter, and then we have a larger diameter, and we have a longer carbon nanotube than them. But we do not have the same purity. Their purity is better. Why? Because we still have the catalyst inside our carbon nanotube. And that's depend on the end stream application. If you need it for battery, we need to get to this purity or higher. And therefore, my team developed a recipe of recovering the catalyst particles out, meanwhile keeping the carbon nanotube intact. So that we can get to higher purity out of the process. But nevertheless, now it will going to be more expensive. It will not going to be the same cost that you earlier have seen with the process, but every process is going to have its needs. So I'll just show you details. Now let us compare this technology with the existing carbon nanotube manufacturing process. And this is, by the way, even having challenged by RISE. I presented RISE University headquarters, some of those. So our advantage, we are now the only existing technology use CO2 to make carbon nanotube. All of the others are CO2 emitters. Okay, this is the first one. Second one, we are producing hydrogen, only the pyrolysis, which is producing hydrogen, but the others not producing syngas. And pyrolysis only hydrogen, not syngas. So we can be integrated in a processes using syngas, but not the pyrolysis. Okay, so and then we have the energy requirement. If we do it around this photothermal, we're close to zero, and then so on. That's a lot of advantage in terms of how we can deal with it. But our carbon nanotube is a green carbon nanotube. And our hydrogen is even greener than the green hydrogen. And therefore, we make this artificial color code. We call it gold, even though other people have a different classification of gold hydrogen in the process. So where is this carbon nanotube going to go? What market it will going to be utilized? These are the significant existing markets, by the way, for carbon nanotube. And we tested some of them. We have gone very deep in the entire industry process. And who are the major producer of carbon nanotube now globally? The major producer of carbon nanotube globally is in the electronics, and LG, by the way, is the major producer of carbon nanotube. So here you remember that the monolith company that the Department of Energy loaned it $1 billion in order to make it, to move the pyrolysis process. And the statement from the Goodyear. They said that as the only US headquarter tire manufacturer, it is especially rewarding to be in connection point significant US innovation with Monolith, and they were partnering with them. This is the letter that we received from Goodyear in 2021. They are the one who called our carbon nanotube green carbon nanotube. They use it through a company in Austin called Molecular Repart Design. They blend it and they give it to Goodyear. And Goodyear issued this certificate that they think Texas A&M technology is the most suitable for the green and for the electric vehicles that they would like to use in the future. And they said that it's very interested in working with us in terms of R&D to develop this material to be part of the rubber industry. So what is next? Now, as academia, we reach our limit. Okay, so the commercialization now, it has to go to the tons levels. And even a different reactor technology you have. I presented you several reactors from the micro scale all the way up to kilogram scale. Each one of them is a different reactor technology. I'm not going to say what it is. We are working on the second level of those reactor technologies. And now both Qatar Energy and Shell waiting for Qatar Foundation to give them the license of this technology. Texas A&M, as per their agreement with Qatar Foundation, the entity hosting us in Qatar, gave the rights of whatever IP for research they co-funded to them, not to Texas A&M. So now for time, I'm not going to say what is the time because we are recording, okay? We are waiting for them to give this license. They make a joint group and they are coming to commercialize this technology to be part of the gas processing research, but it has several elements that we are working on it. And obviously because of has all of them. But the interest in the industry side is going beyond different groups who look at it in different, even the microchips in terms of utilization in the microchips industry. Finally, I'm going to tell you, this is not only the story. So we work with the industry very closely to develop this CO2 utilization. You remember that DMC, which is a simple chemistry. I'm not going to burden you with all of these details. I will take you to something that's a conclusive of it. So what we are trying to do, how we could really make it a CO2 utilization technology and how we can overcome the burden of commercialization. Here we are using CO2 and methanol in order to produce a very important precursor of the process. My team worked with it with Shell. We worked for a long while, and what we have reached, we reached to something very unique. So the process is reversible type of reaction governed by the equilibrium. This is the problem. The yield is very low because it goes back again, but it is a CO2 utilization process. And we developed jointly with Shell the process on how to handle it, to make it irreversible so that we can increase the yield by streaming the water. And that's also another level of collaboration with industry in order to scale up this technology, to take it to a higher level. And now we have a patent in this cycle that's been approved, but the technology now in the pilot scale level of operation, that's jointly project with Shell, actually led by Shell in those work. So as a team, and that's my research team, we need to educate the industry on how to use our technology. Our technology is not one design, it's not one setup. Our technology, if you need it only to produce carbon nanotube, completely different if you need it to integrate it within a gas processing plant or a chemical plant. And each plant has its feature. It depends on the feed gas coming to it, and it depends on the product gas and the quality of the product gas you need. So as a startup, we are working with those companies, and the startup have a number of my researchers, which is our unique group that's only the small group that's in Qatar. Those in College Station are not in the photo. You can see them over there in the photo. But now, those who work on the projects that I presented to you, this is where they are right now, okay? As well dispersed. I'm mostly in the industry. I'm more in the applied side, but some of them in academia as well, global-wise. That's working on it. Also, my collaboration with different academic group around the globe, and I hope that's we're gonna be able to extend it to this collaboration with Kevin and with the team here, with all of you, to work with different areas. We work in different projects. We address different, but the uniqueness also work with the industry. Those listed here work directly in those projects as BIs. Okay, and that's the way we're addressing. So at the end, thank you so much for hosting me again. I'm sorry if I took longer than expected, but this work funded many of it by Qatar National Research Fund, as well as by different entities from the industry. You can see Shell, you can see Total Energy, you can see Qatar Energy now, which is Qatar Gas, become Qatar Energy, and Qatar Energy LNG, by TEAS, and TEAS is the Texas Engineering Experiment Station, SASO, Oryx ETL, and others. Thank you so much. Appreciate it.
We will take questions. If you, since we're past the hour, if you need to leave, feel free to just get up and leave. But we'll go ahead and take some questions. We'll take questions alternating between the room and online. So go ahead and start with the room here.
So I had a question about
yes.
The as economies of scale when you get to a $10 per kilogram carbon nanotube. So is that what you're saying you can actually produce it at, or that's the value that you think when you get that's I couldn't know that was a production price or
excellent question. Yeah, excellent. Both of them. So first of all, our technology at the large scale, we will gonna deal with a significant amount of CO2. All right. So we have seen, for example, only in those midstream plants in Qatar. This is the CO2, and this is a semi-pure CO2, by the way. This is above, in many cases, above 99%. And this is millions of tons per day. So if you deal with putting plants in those type of infrastructure, yes, our technology gives two advantages. It is lower in cost because it uses the existing energy of those plants. And then if you use this amount of CO2, yes, you are going to go to a very high productivity in terms of the multi-wall carbon nanotube of the process, and therefore the cost will significantly drop exponentially as a result of the combination of both the quantity that we could deal with in the process, as well as the availability of those amount of feedstock that does not exist anywhere. But it comes to the question. If we need it for a process that's only need the carbon nanotube, they don't care about whatever, they don't want to integrate it in any, and we got a lot of companies that showed interest to license it in those fields. Then the design will be different, the size will be different, because the resources will not gonna be able to integrate it back again. The cost will gonna be different, and the formula will be different. So this figure is specifically for those with that infrastructure of gas processing plant. That the big plants that they can use whatever syngas we produce in the process downstream, as well as they can feed us with even energy to be integrated from their existing infrastructure. That's this integration, and that's in the GTL paper. We have shown that exactly how we can build this. We are not changing anything. It is added value to the process. We will take and we will feed back again to the process, how that will gonna impact the existing process in terms of energy and process. Those are the type, because we can go to a very large scale in terms of productivity of carbon nanotube, and it will be much lower cost. And also in terms of capacity, we're gonna significantly drop the cost of the process.
That follow-up.
Yes, indeed.
So when you get to that cost, what is it replacing in the tire? Is it replacing the steel, or is it replacing
Carbon black.
rubber? It's replacing the rubber.
Yes,
Okay.
carbon black.
So what's the
carbon black?
Okay,
Yes.
that's
Yeah, black, yeah.
Not really.
Yeah.
okay.
It's
a filler.
Used to
Yeah.
stabilize and prevent oxidation.
Yes.
Right, sorry.
Yes.
Right.
Yes. And by the way, it's a big deal. So when you count it, it's a millions of tons. If you replace even third of it. So, but you cannot compete with the cost now. So in terms of the existing cost, you cannot compete, because the carbon black is much. Yes, please.
Yeah, very good talk. I mean, switching, from the CO2, capture CO2 to make the syngas and the carbon. Okay,
Yes.
This CO2 to carbon is a reduction reaction. So you're using a lot of catalysts.
Yes.
Consume the catalyst, right? So I don't know how expensive the catalyst they're using. So another key question is that when you make the carbon, so maybe the catalyst will get toxic. So that how often you need to change the catalyst? You think that if you catalyst the most expensive stuff, if you make the carbon maybe very toxic for my understanding.
That's a very good question. First of all, it is almost sacrificial catalyst relevant to the cost of carbon nanotube. And the way this is a pattern. You remember we switch from a catalyst to protect itself from carbon deposition to a catalyst that aim to make carbon. So this is our patented catalyst. It is much cheaper than whatever the commercial catalyst. We start with the baseline over here. And when we compare its cost with the carbon nanotube, with whatever price, even for the $10 per kilogram, yeah, it's sacrificial type of catalyst. So, and we are not worried about, it is all about, it is steep growth mechanism. The catalyst is a part of the filler of the carbon nanotube. If you remember the TN, high resolution image. So it goes, we need to enhance its engagement in the process. So it will gonna go with the carbon nanotube. So the catalyst, we are not going to regenerate the catalyst or the catalyst, and there is none. Until now, what we have done it in almost different concentration of CO2, but no sulfur. So we cannot, when you say poisoning the catalyst or toxic the catalyst, so yeah, I guess maybe inert material like sulfur. I cannot confirm. We don't know how the catalyst will gonna deal to sulfur because we haven't tested. Not because we don't want it, but because our facility do not allow us to do whatever that percentage that we need in order to verify the process. We are trying to do it with a third party. But other than that, we haven't noticed anything. So it is all about the protocol, because our process until now is semi-batch. It's a CVD, chemical vapor deposition process. So we have to keep this until this carbon fill the full tube. That's it will be full. There is no space, then we stop it. And then we discard the carbon. So it's still to go to the moon. The other reactor that we are designing now, for that very large scale those guys are looking for is a different technology. Sadly, I cannot talk about it now. Okay, it shows that we have to look at all of those scenarios and we have to look on how to sustain this catalyst in a continuous mode so that we guarantee the catalyst will gonna go and make this structure of the carbon nanotube because we're not gonna be killed at the beginning. That answer your question? Okay, you're welcome.
Okay, I'm gonna check in with our online audience to see if you have any questions. Feel free to unmute yourself now and ask. No.
Okay.
No. Any more questions from the room?
I have a question.
Yes.
So you produce carbon nanotubes from the CO2 and methane. After that, the syngas goes to Fischer-Tropsch reaction, produce SAF, right? But then the SAF has no aromatics. Then you need to blend with some seed
That's excellent.
to be used as a heat fuel.
Okay, very good, very good. So again, until now, when we used it as a GTL, you remember the whole thing started from my research team interested in the GTL. So what I presented to you, how we use that liquid fuel that's coming from the GTL, that's ultra clean fuel, look like water, smell like water, how we could really certify it for aviation industry, or diesel, how we blend it, how we do a lot of things. Specifically, we focus on the aviation fuel, which is, we never at that time expecting there's something called SAF will come. When we started this project in 2009, with Shell, with Rolls-Royce, and with those, not even SAF, it wasn't even, the name wasn't there. But fortunately, we accumulated a lot of knowledge. So then we moved to the Fischer-Tropsch. And the Fischer-Tropsch is a catalytic, the reactor design, it's the heart of the, because it's the one take the gas, make liquid. And then we came to the reformer. We knew the reformer is the most critical element because it's the most energy intensive of the process. So we knew in order to make a significant change in the GTL process, we have to address these carbon emissions. That's by the reformer. And we have to lower the energy intensity of it. So we focused on the reformer, then we went back connecting the story. Okay? So in the reformer now, the minute we use the CO2, we produce syngas. Is that syngas necessarily go to GTL? Not necessarily. It can go to methanol, can go to ammonia, it can go to whatever. That's urea, downstream type of process. But nevertheless, if it goes to GTL, our process is much better than the existing current GTL processes. Because we sequester the syngas we are produced is carbon negative syngas if we use CO2 for the reforming process. From the beginning, we started with negative, not even with zero. Okay, then until now, the sustainable aviation fuel, we cannot, in the fuel, we cannot use hydrogen in the airplane. We know we need billions of liters, okay, in order to meet the market demand of SAF. So it's still Fischer-Tropsch is the way, even if we get the hydrogen from the electrolysis, okay, and we get whatever the hydrogen in the process, and then we get the CO from the water gas shift reaction. When we take and make liquid of them, we need Fischer-Tropsch. So our knowledge in both in the Fischer-Tropsch and how to make those fuels and blend them adds a significant value for us, besides the fact we decarbonize the main elements of the process. So now we are dealing with all of those. When you produce a fuel similar to any synthetic fuel is not necessarily need the density. We have deficiency in the density because it is highly paraffinic. So the density normally by the aromatics, by the other components like naphthalene existing in the crude oil boosts the density. We do not meet certain properties. We normally blend them with the conventional fuel in order to get there, and therefore the certification is 50/50. Okay, so we still need to do, but this is an existing know-how. The industry know it and know how to blend it. They certify already synthetic paraffinic kerosene, so we have no problem in that end. So our end is how to rationale for them. We can still start from natural gas, and we can decarbonize, and we can add economical value. We can guarantee the CO2 fixation, and at the same time, we add you an economical value of carbon nanotube. You can sell it and make money out of it, which is not the original.
Any final questions? What else would you like to leave us with?
So I guess, yeah, we are still at the beginning of the road. This area, you are doing top-notch type of research here in terms of the CO2 capture. This market is a huge market, and the demand for it will gonna keep growing. But we need to develop those technologies in a fast track, because unfortunately, we may be at this moment of time, we are getting closer, if you're not go there, to the irreversible damage to our environment. So if we need to sustain with the existing energy sources, and it's always, and that's what I said in the COP28 in United Arab Emirates, it is energy security with affordability, okay, with whatever we have right now in terms of the technology status. So we cannot say to the people to switch whatever fossil fuel you have, do whatever. We cannot, because that's energy security. There is no life even. In many places, people cannot even survive. But we have to ensure that we can really speed up the technology that address our existing resources. And I guess that's something we could really work on. We have brilliant students. You see, the whole thing wasn't the original 6 million proposal that we won. And it's a very competitive type of funding, by the way. It wasn't there. A curiosity of a student, okay, just opened the way for us to get to something we never encountered, and it became the major outcome of the project. It was never there, and it was never intended to do. We are trying to avoid carbon. So we encourage those students, be very open and never, and that's what I teach my team, whatever idea, and don't even feel shy to ask any question. There is no silly question. Ask and get curious and do things as people, and that's open the road for it. And thank you so much for hosting me. It's a great pleasure.
Yeah, thank you.
Thank you. Thanks a lot.